Hello everyone! Welcome to our talk on resonance basics. Before we get started, I should note that these are some things that you'll need to know for this to make sense. You'll have to know Lewis dot structures and how those work. Also, formal charge is actually really important here. You'll want to know also how to write organic structures in line bond form because that's the most commonly one used, so that's what we're going to use in all of our examples. So if you're not feeling really great about that, you might want to practice that a little bit more before you get started. You may have heard the term resonance before in Gen Chem, but we're going to go into a lot more detail and to make it very specifically organic. So it's going to be important for me to make sure that I explain it well enough, and also important for you to make sure you go over it until you understand. And there'll be lots of practice along the way. So first thing is we need to talk about what resonance actually means. So resonance has to do with something called delocalization. So normally you think of electrons as being on the atom, right? You draw the Lewis dot structure and they're attached to whatever atom you draw them on. But actually some electrons are not tied. So delocalization means that electrons are not tied to one atom or bond. So we would think of that as if they could move around. They're not actually moving, but we're going to think of it that way because it makes it a little bit easier to think about. So now you may be asking, why is this important to me? Well, basically, it's because molecules with resonance are more stable. So resonance is something that we can use to recognize molecules that are going to be more stable. This is a fundamental law of thermodynamics that things like to have a lower potential energy. That's where that comes from. But it's also going to be good to know so when we're trying to choose between forms, we know which form something's going to take or where a reaction might want to go forward. So again, this is going to help us predict behavior. So for me, if I'm going to get into something, I want to start with what's it going to help me be able to do. So we're going to show some examples here. First off, these are all three molecules that have resonance. And what we're going to ask you to do, say on a quiz or a test or something, is draw all the significant resonance structures. So you need to come up with how many there are. You want to label each structure in the part with letters and put a star by the most significant contributor. So the goal there is figure out the most significant contributor, and then draw the resonance hybrid for the molecule. So those are three things that we're going to be able to do by the end of these talks. But of course, we're not quite ready for that yet. I'm going to have to tell you a little bit about the strategy to do these problems, but this way you at least know where we're going. So first, we're going to talk about what you need for resonance to occur. Where would I look if I was looking for resonance? So the first thing that we need is extra electrons. The extra electrons mean that they're not in a sigma bond holding the molecule together, but that they could actually be delocalized. And electrons that are delocalized are always going to be in a p orbital, but that's something we can talk about later. So when I'm thinking about where extra electrons are, they're usually going to be in a lone pair. That may or may not have a negative charge. It doesn't have to have a charge, but it's going to have a lone pair for sure. Or the other place they can be is in a multiple bond. That would be like a double bond or a triple bond. So these are the places that you could have extra electrons. That's what you're looking for. So once I know where there's some extra electrons, I also need a place for those electrons to go. So if we're thinking about them moving, where else could they be on that structure? So usually this is going to be a positive charge or a multiple bond. So the multiple bond actually has to move those electrons out of the way, but we'll talk about that later. But a positive charge is just an empty orbital, so that makes sense that usually they can go to a positive charge. So this is the summary of what you need for there to be resonance. But before we get started, we also need to talk about the rules for going between different resonance forms. So let's talk about those rules. So the first thing is there's no moving atoms, only electrons. So the electrons are delocalized, but you can't be moving hydrogens around. The connectivity must stay the same. So this means you cannot break a sigma bond, and also you can't jump atoms. So you can't have electrons go from way over here on the left side of the molecule to way over here on the right side of the molecule. They would not be able to reach that far. They have to be sharing with at least one of the same atoms. So the next rule is that all of your resonance structures must be legitimate structures. Remember, legitimate just means it's all octet unless there's exceptions like boron or something. All right, so that means you cannot have any carbons with more than 8 electrons. And then also you should never have 5 bonds to carbon. If you ever see that, that's totally wrong. The number one rule that everyone usually remembers after organic is only 4 bonds to carbon. So that's going to be true. It's also going to be true for nitrogen and oxygen because they're in the same row on the periodic table. But usually carbon's the big one. Before we move on, I should mention that we will see a common exception to rule number 2, and that is the carbocation. A carbocation is a carbon with a positive charge, and that can only have 6 electrons. So we will see that. So if it starts off with a carbocation, then that would be legitimate. But if it doesn't start off with a carbocation, you usually don't do that. So the last rule of the resonance structures is that the overall charge of the molecule must stay the same. When you draw the different structures, they're going to have different formal charges on the atoms. That part's going to change. But the overall charge should stay the same. So that's a good way for me to go back and check my structures at the end, is I should make sure they all have the same overall charge. So now that we've gone over all the rules and things you need, let's go ahead and go back to those examples that we saw before. So now I'm going to work through some of these examples. Now I recommend that as I do this, that you go ahead and do the examples with me. It's really fun to watch someone, but it doesn't really stick in your brain very well unless you write it down yourself and think about the problem as we go. So I'm going to ask you some questions so that you can also help me on this problem, and it will be best if you will pause the video and work on those as we go. But regardless, go ahead and write these down. So pause the video and write down all 3 examples. Leave some space in between, especially for example number 1, because you'll probably want to write some other stuff. You don't have to write all the words right now, but definitely write down the examples. So now that you've gotten those written down, let's talk a little bit about them. So as you can see, the process is going to be, I'm going to be looking for extra electrons, so like lone pairs, multiple bonds, and I'm also going to be looking for places for electrons to go. So positive charges, multiple bonds, things like that. So those are something you can see in these structures. But the other thing is I'm going to start moving electrons around. And whenever I do that, it's going to be really important that I make sure I'm not breaking the rule about never having 5 bonds to carbon. So something else I really need to be able to see is where the hydrogens are. Now, as you practice, you're probably going to get used to the idea that oh, hydrogens are always here and not try to do anything crazy. But when you first start, I think it's hard to remember where they are. So what I would do is, until you're comfortable, go ahead and turn these structures into the expanded form. Line bond is a little bit hard to work with at first, and we're going to like it later, but for now, it might help you to draw that out, just for your own good. So now let's take a minute and have you draw the expanded forms off to the side for each of these 3 examples. Somewhere off to the side. Don't maybe put them in your space for your answer, because this would not be your final answer. You're going to have to draw your final answer in skeletal or line bond form, but put it somewhere off to the side just so you can see where all the hydrogens are. So pause the video and do that. So hopefully for your first example, this is what you got. Notice every carbon has 4 bonds to give it an octet, except the carbon that has the positive charge. The only way for carbon to have a positive charge is to have 6 electrons. So if we were going to do the formal charge math, we're going to say 4 minus what equals positive 1. Well, so hopefully we recognize that should be 3. So that means we have to have 3 bonds, and 4 minus 3 will equal 1. So that means the extra bond is going to be hydrogen. So now let's look at the other 2. Hopefully you got those. They should look like this. So as we see, we've got this one here in the middle. We've got another carbocation, so that's again going to be 3 bonds, just like the one before. Every C+ is going to have 3 bonds. That will always be the same. So then if we look here, nitrogen only has 2 hydrogens. That's normal. It has an octet because remember it has a lone pair there. So then the last one, everything has the right number of bonds. We've got all the carbons have 4 bonds, and the oxygen only has 2 bonds. That's totally fine because remember oxygen also has 2 lone pairs. So we put the lone pairs there. That'll probably help us out. So now let's look at these examples. I'm actually going to start with number 2 because it's a little bit more simple. So looking at number 2, we're looking for where electrons are. So where do we see extra electrons? Right, so they should be here in this lone pair. If you look on nitrogen, that's the only atom that has a lone pair, and we don't have any negative charges or anything like that. So that's where we're going to start. And then where is a place for electrons to go? Right, we've got a positive charge, and note the positive charge is right next to those electrons. So what we're going to do is I'm going to draw an arrow to show that those electrons are moving basically. Instead of being on the nitrogen, they're going to move and be part of this bond here in the middle. So I'm going to draw them from the electrons to the middle of the bond. So now let me draw what that arrow is going to mean. So what is that going to mean for my next structure? So when I'm drawing my next structure, the first thing that I want to do is just copy all of the atoms, all right? Because none of the atoms can move, right? So let's copy those again. Perfect. All right, so now we're going to keep all of the single bonds the same, but we're going to change and not draw that lone pair, and we're going to draw a double bond in between the nitrogen and the carbon. Perfect. So now the next thing we want to do, now that we've gotten we've copied it the same with single bonds. We've added any double bonds or moved any things we needed to move. The last thing we need to do is figure out what happened to that charge. So if you're looking at this atom here, carbon now has 4 bonds. So what would be the formal charge on that carbon? Right, it's going to be 0 because 4 minus 4 is 0. And then what would be the formal charge on the nitrogen? So nitrogen before it had the lone pair was 0, but now it doesn't have that lone pair anymore. So now it's going to be 5 minus 4, which is plus 1. So now that's where the formal charge is going to be. So now that structure is done. So then the next thing we want to do is, as I said before, your final answer can't be in this expanded form. It has to be in line bond form. So what I'll do is I'll just take this structure and draw it on the left in line bond form instead of in expanded form. So pause the video and try to do that. So hopefully this is what you got. So as you can see, basically all I did was take away the hydrogens. I put the charge on the nitrogen like I'm supposed to. And now you can see why I always talked about circling the charges before. It helps to have a circle because now a line means it's a bond to carbon. So instead of a negative charge, you might think it's a line to carbon. So that's why I'm circling it, but I just circle the positives as well. So the next thing I would do once I'm done with my first form is I would see if there's any other place that I can move electrons. So then the place where I have extra electrons now is this double bond, but can I move that double bond? So I can't move it back to the nitrogen because if I do, that's just going to take me back where I started, so that's just not going to help me. I could try to move it to the right like this, but if I do, that's actually not going to work out. Now, if you look at the structure on the left, obviously it seems like it should work out. Like if I was going to do that, it would look like this. And that seems like maybe something you could do. But if we look back at the structure on the right, then that would actually be the same as drawing it this way. So now you can see why there's a problem. So the problem would be that this carbon here would have 5 bonds because it has a double bond plus the 3 hydrogens that are still there. And that's why you have to know where the hydrogens are before you can really get this to work out. So you need to practice with that. Another way to show that if you're only using line bond form is sometimes what I'll do is I'll put like fake hydrogens on there. So on my original structure, I would draw them like this. I'll just draw little ticks where the hydrogens would be. So I draw that there on my original structure. And then I can see that there's 3 hydrogens on there. So whenever I draw this red form, I would know like, oh, that's a double bond plus 3. That's going to be too many bonds. So that's how I know how to stop. So now that I know I can't go that way, would I be able to go and move the electrons to the carbon on the bottom? No, right? Because obviously that's still CH3, so it's not going to be able to go that way. So I'm not able to go left, I'm not able to go right, so that means this is actually my only other resonance structure, and I'm totally done drawing all the significant resonance structures. So this one only has 2, so this would be A, that's the first form, and this would be B, so that's 2 resonance forms. So with that, I'm going to go ahead and stop for this video. I don't want it to get too long because YouTube doesn't like that, and probably you could use a break. So don't give up though, we're not done yet. So we're going to go on to the next video, which will be part 2 of resonance, and we'll do more resonance examples in that, and then we're going to go on from there. I'll see you soon.